Our next speaker is Professor Umesh Waghmare from JNCSR. So he is currently the president of Indian Academy of Science. Um, so Professor Waghmare is quite well known in his field. He is of course members of all the academies in India and also recipient of Bhatnagar Award. Um, so today he is going to talk about uh, this metavalent bonding origins of unusual properties of group 4 uh, chalcogenides.
First of all, it's a pleasure to be back here in Math Science, and I wish to thank the organizers, Arijit and Sayantan, for the invitation and hospitality. Also, I wish all greetings for the 60th year of Math Science and wish lots of growth in terms of scientific domains and quality of work in the coming decade. So I'm going to talk to you about some work which my student Ragya Arora has completed in the last 2 years. And it's a problem which is of interest to chemists, physicists, and technologists. Materials are chalcogenides, and some of you may be wondering what chalcogenides are. These are basically elements in the group of sulfur and selenium and tellurium. In fact, some of these materials relate to what Shiraz talked about as being topological ground states, gapped states. And the bonding in these materials has been a subject of great interest to physicists and chemists over the last 50 years. Yeah? So it has been an interesting exercise, and by the end of this talk, you will see how a physicist can use basic ideas like spontaneous symmetry breaking in understanding chemical bonding, which is not understood yet in these materials, which are of technological importance. So let me get going. Yeah. So lead telluride is one example of this material. Lead is an element which belongs to group 4, which is the group of silicon, germanium and all. And tellurium belongs to group 6. They are called chalcogens. You will see they are really interesting systems. You will, I'll hope to convince you through this talk. So let me start from some high school chemistry, particularly about bonding. And if you remember, if there is a transfer of electron from one atom to another, you get ionic bond. And the crystals which you make from ionic bonding are typically very large band gap insulators, and they have very low electrical conductivity. The second category is covalent bonds, where 2 electrons are shared between the neighboring atoms. And these crystals tend to have slightly smaller band gap, electronic band gap, and hence they have relatively lower electrical conductivity than metals. But much higher than the ionic systems. Sorry, this button I'm still getting used to it. The metals on the lower left here involve electrons which are shared between lots of atoms at the same time. And as a result, the electrons are highly delocalized, giving you very high electrical conductivity. And of course, you also have hydrogen and van der Waals bonding. Chemists like to call them as weak bonding, meaning the energy scale of this is about a few millieV, whereas the energy scale in the ionic case is about 10 millieV. Okay, so that's the range of energies spanned by this different chemical bonding. And the key point is each bonding is responsible for different properties of a given crystal or a material. Yeah. So indeed, if you want to develop new materials for technologies, you really need to think using ideas from physics, chemistry, and engineering, because chemistry is what drives many of these properties. So phase change chalcogenide materials. An example here I'm giving you is germanium antimony telluride. It's called GST system. These are very fascinating material. Yeah? In the time scale of 100 nanoseconds, they can go from amorphous phase. Amorphous means there is no periodic long-range order in these materials like glass, to a crystalline phase. This is actually sodium chloride structure, our rock salt on the dining table. Yeah? So this transition occurs in the matter of 100 nanoseconds. Not only that it's an interesting phase transition, but the properties of the two states are very different. The amorphous phase is covalently bonded and it's very transparent with large band gap. And that chemical bonding is very easily understood, but the crystalline phase is very different. In fact, the question of today's talk is what is the nature of bonding which governs properties of the crystalline phase. So because there is a huge contrast in the properties in terms of optical behavior, electrical conductivity, this phase transition is used in making real computer memories. Yeah? Because the time scales are also reasonably good. But if you want to develop better and better, faster memories, you really need to understand these materials from fundamental point of view. So clear definition of this mechanism is lacking, and the nature of electrical and chemical bonding, the fundamental mechanism itself is unclear and has occupied physicists and chemists for 50 years. So why are these materials so interesting? This is to get you interested in knowing about them, okay? The first one is these materials are some of the simplest ferroelectric material as shown on the lower left here. Ferroelectrics are essentially electrical analog of magnets. Instead of having north-south pole, they have positive, negative dipoles in them, which are spontaneously present. And in this talk, you will see why they come about in these simple materials. The second is thermoelectrics, very fascinating materials. In fact, there is no symmetry restriction for a material to be thermoelectric. All materials are thermoelectric, but these chalcogenides are exceptional. Yeah, and the reason is, you will see for the thermoelectric material to convert waste heat into electricity in efficient way, what you need is the material should have very low thermal conductivity, otherwise the heat will just pass through to the cold side. It should have very high electrical conductivity because you need to generate electrical current out of it. And at the same time, it should also have very high Seebeck coefficient, which is the thermoelectric effect. Yeah? So high Seebeck coefficient requires a material to be semiconductor, high electrical conductivity requires a material to be metal, and low thermal conductivity requires a material to be a glass. In the same material, you want all these three properties. And in fact, these chalcogenides are one example of it. Yeah? So we will develop very sort of basic understanding about how this happens. The third one relates to Shiraz's talk, where he talked about two-dimensional gapped topological states. And these materials are actually three-dimensional gaps topological insulators. And if you cut a surface out of them, the surface is always metallic, just like the edge states in the integer quantum Hall effect. Okay, so these are materials. In fact, to design topological insulators also has been a challenge because chemists don't really understand the bonding and the nature of interatomic interactions in these compounds. So the first thing about these materials is the basic 8 minus rule, which we study in high school chemistry, is violated in it. Right? You need 2 electrons per bond, typically if it's a covalent type bond, and these are definitely materials which violate that. Here is an example of germanium selenide, which is in the structure called zinc blende structure, similar to silicon or gallium arsenide. And in this case, there are only 4 bonds per atom, and there are 8 electrons total for pair of 2 atoms. So there is no violation of 8 minus n rule. But if you take chalcogenide in the rock salt structure, indeed you have 3 electrons each per atom. So you have 6 electrons and you have 6 bonds. So it's essentially half-filled state. You have too few electrons to make up those bonds. Yeah, and that's why this is a key signature of these compounds, that effective coordination number is too large for the number of electrons they can afford. Okay, so initially this was in 1970s. Okay, this is what I said when I mentioned that. I'm sorry, I think I'm still getting used to this. Yeah, okay. So these materials have been intriguing for last 50 years. Initially, the physicists like Lukowski and White looked at them from the perspective of using them as semiconductors. That's when people were interested in having better and better semiconductor materials. And they thought that the bonding in this material is like benzene. Again, something we know from high school days, where you have 2 structures of benzene which are equivalent and same symmetry, and if you sort of take combination of them, you get delocalized electrons in the pi bonding clouds. So in these compounds, this is inorganic analog of these resonant bonding materials, where you have 6 electrons and 6 bonds at a time. Many of them are not even filled. So there are many structures, infinitely many structures possible for those configurations, and the linear combination of them will give you the resonant type bonding. So that was the belief in early 70s, and also in 2008, this was the mechanism people believed governed interatomic interactions in these compounds. Then there was a PhD thesis by Peter Littlewood from Cambridge, and he showed that actually these materials are closely linked to what are known as spirals unstable solid, meaning these materials have very high degeneracy, electronic degeneracy in the ground state, which means the ground state is not going to be stable. It will break its symmetry, and that's when you get basically this dimerization. Some bonds become small and some remain large. And with this, Peter Littlewood tried to explain these large electric dipoles which develop in these materials. Yeah? So this was in also late 70s. And Peter Littlewood actually was really brilliant. He developed a very simple model to understand and explain many of the observed properties within that simple model. I will convince you by the end of the talk that this is actually correct in spirit but wrong in technical details. Yeah, so we'll develop a correct picture of this. Yeah, okay. So there are 2 properties I want to introduce to you about these compounds, which are very basic properties, but you know that they will explain to you why these materials are technologically interesting. The first is called Born effective charge. So suppose you have sodium chloride crystal. Sodium is +1 charge, chlorine is -1 charge. If you displace sodium ion by distance u, you will develop an electric dipole moment, which is charge of sodium times u. So in these compounds, if you have germanium telluride or lead telluride, tellurium is 2-, you will expect. So bond charge should be 2-. But if you actually estimate it, it comes out to be, I'm sorry. The bond charge is actually -8. Yeah, this one. That's totally anomalous. You can't expect -8 charge on an ion, where you expect normally by looking at the static chemistry, the charge should be -2. So where does this very anomalous bond charge come from? In fact, physicists would like to look at it as the measure of long-range Coulomb interactions in the crystal, which are responsible for mathematical non-analyticity in the spectrum of vibrational modes, which is called LOTO splitting, which basically gives you the measure of this interaction. Second is Gruneisen parameter, and this is basically logarithmic derivative of vibrational frequency with respect to volume of a crystal unit cell. And this parameter typically is much smaller in most compounds, and in these compounds it tends to be bigger than 8. It's a dimensionless number. It's also very anomalous. Yeah? Why is this very important? See, electric dipole moment is important in ferroelectrics. Here it is crucial in thermoelectrics, and I'll explain to you. Do you know which is the crystal or material which is best conductor of heat? Heat. Maithili talked about heat conduction equations, right? So the best material is diamond, not copper or gold. One would expect that they are the best conductors of electricity, but their thermal conductivity is 10 times smaller than diamond. And the reason for it is the diamond is the highest material, the velocity of sound is highest in diamond, and those are the carriers of heat. Because when you heat up a material, it's the vibrations which carry the thermal energy, and the carriers are acoustic phonons, okay? Acoustic phonons or sound waves are nothing but the strain waves or volume dilations and contractions, and that's why this parameter measures how strongly the sound waves couple with the other vibrations in the crystal. And as a result, if this parameter is large, you have highly nonlinear vibrations which basically dampen the flow of heat, and you get a very low thermal conductivity. Yeah? So this is why they are really interesting and relevant to the three classes of technologically important materials I talked about. So until the beginning of this century, these materials were classified more in the property space rather than any microscopic mechanism, okay? So these are the properties: electronic conductivity, effective coordination number, optical dielectric constant, which is essentially square of refractive index, bond charge, which I defined, Grunison parameter, also something I defined. And you will see these metavalent crystals here fall in totally different category. Metals are on the right hand side and the covalent and ionic crystals are on the left hand side. So looking at these properties, these people said, look, no bonding seems to explain this bill of properties that one has in these compounds. Indeed, they break in a very unique way too. There was an experiment based on atom probe tomography which tried to study how these materials break when you apply stress to it. And there also the atomic mechanisms here involve many bonds breaking at the same time. So there's a fundamental difference in the way in which these bonds break. Okay, so to summarize these properties, there are three features which are very special about these compounds, which differentiate them from the resonant bonding as well as basically other types of bonding. One is the bonds are very soft, so vibrational modes are very low frequency. Grunison parameter is very high, means vibrations are highly nonlinear. Third, optical polarizability is very high, means the electrons are highly delocalized. They give you huge dipole moments when you apply electric field. Yeah? And in this sense, you have basically delocalization of electrons as well as structural distortions which come about to give ferroelectric type things. So there was an attempt in 2018, and this is where they proposed the name of chemical bonding in this as a new type of bonding called metavalent bonding. And the idea was they looked at on the x-axis number of electrons shared between the two atoms, and on the y-axis number of electrons transferred from one atom to next. And you will see metals are here where both numbers are relatively small. Ionic ones involve complete electron transfer. Covalent means complete effective sharing of electrons, and resonant is even above that. That's where you have, of course, sharing of electrons through sigma bonding and also pi type of delocalized electrons. And the metavalent ones, these are the chalcogenides that I'm talking about, fall in between this, nearly in the centroid of this triangle of the three conventional bonds. Yeah. So indeed, this was convincing enough that something is very different here, or a sort of mixture between different mechanisms. Sorry? Yeah, no, ZT. Thanks, you have a very fine attention, Hassan. ZT is the figure of merit of thermoelectric materials. It tells you how efficient these materials are in thermoelectrics. And indeed, you will see that only these have a ZT which is significantly higher than most other compounds, where it's less than 0.1. Yeah, thank you. Okay, so this sets the stage for what we set out to do. Basically, the metavalent bonding remained defined essentially in the property space, and our goal was to understand it in a fundamental way, possibly using the language that physicists are used to. Yeah? So that's where we start. So the first thing physicists do, and it came up in this meeting earlier too, we are good at modeling, like Gautam Menon said. Yeah? So what can we start with to simplify this type of materials first? Okay, so what we do in our plan is basically evolve metavalently bonding states adiabatically, starting from different types of bonding like ionic, metallic, and covalent bonding. So this gives us a very well-controlled access to how this bonding changes along these continuous paths. Yeah, and it also tells whether they are qualitatively different or not, or it's just an extension of one type of bonding. That's the approach we take. The methods we use, I won't go into these details, but just to tell you that these are called first principles calculations, means we assume nothing from experiment at all. Only thing that comes here is the values of Planck's constant and mass of electron, which are the fundamental constant, and we use basically Dirac equation or Schrodinger equation depending on what may be relevant. And these are the softwares which are mostly open source software which are available. And you will be amazed that most of the calculations I present here can be done on a laptop using these tools. So they are really powerful tools today. Of course, people do use them on high performance supercomputers, but there the scale of those problems is very different. Here the idea is more relevant than the scale of the problem itself. Yeah. So our first step is to identify something simpler, which is higher symmetry possibly. That's the way we would like to think about how this bonding comes in. So starting from the structure of lead telluride shown here, this is the sodium chloride structure, rock salt. Yeah. What we do is we replace both red and green atoms by the same atom. And what you get is basically a simple cubic lattice then. And then we say we will average lead and tellurium by something real like antimony. But since we do theory, we can also do alchemy, meaning we can mix two atoms together and develop a hybrid atom, and which is basically this atom. So that's what we did. We did both of these to have a very convincing evidence for our ideas. And this is called as virtual crystal approximation, meaning Hamiltonian of two atoms is averaged basically with the given proportion. Yeah? And of course, why is this a good model to start with? Because it has exactly the same coordination number, lattice structures is the same, number of valence electrons is the same, and they are almost like averages of lead and tellurium. Yeah? So it's a good model to start with. And if you go about it, you find out that actually the parent state is metal. This is, by the way, electronic structure for those in the audience. Usually electronic structure is seen as a band structure, where on the y-axis you have energy of electrons and on the x-axis is inverse wavelength. And these are just different directions in the three-dimensional space. And if you have a gap, you get a semiconductor, which is lead telluride with a small band gap. And this one, the parent structure is metallic with Dirac-like crossing of linearly dispersed bands. Yeah? So indeed, the simple system we thought of as a parent state to these compounds is quite interesting to start with. If you look at it detail, the interactions, electronic interactions are basically sigma interactions between p orbital and also s orbital of lead. In fact, if you use only p orbital interactions, you get an electronic structure which is beautiful. Why am I calling it beautiful? Because if you look at the Fermi energy, which dash line separating occupied states from unoccupied states, you have two types of symmetries in the electronic structure. One is called electron-hole symmetry with respect to Fermi energy, and second is also bonding anti-bonding symmetry. If this band is pi star, the image of it is pi, and vice versa. Yeah? And this is property of just p interactions on a simple cubic lattice. Yeah? And half-filled state. So these already tell you what are the key elements in determination of bonding in these compounds and subsequent properties. Then we move to the next step. Again, I'll skip because I will run out of time soon. But the next thing we do as a physicist is to understand the electronic ground state of the parent metallic structure, and we consider Fermi surface. This is the Fermi surface of antimony in cubic structure, and it's nested. Nested meaning one packet, red packet of the Fermi surface is linked to another blue packet on the Fermi surface by the same wave vector r, gamma to r. This arrow is telling you that. Yeah? And Fermi surface, if some of you have forgotten, is a surface in reciprocal space which separates occupied and unoccupied states. And whenever you have a nesting like this, which means that all electrons on this packet of the Fermi surface can scatter to another packet of the Fermi surface by the same perturbation with a wave vector r. And that's not good because that means that perturbation is going to be unstable. It will destabilize that parent metallic state. And that's what we find if you look at the phonon dispersion, frequency of vibration versus inverse wavelength. There's a strong unstable phonon, which is basically imaginary frequency, means omega eigenvalue of Hessian is negative, and that's the signature of instability in this case, and that basically confirms the picture we have. So what it means is the parent state is not happy and it's going to be unstable, and it needs to break symmetry. In this case, the symmetry will be broken by this R wave vector field corresponding to R wave vector, which is a cell doubling field. You can break symmetry in two different ways. One is structural distortion, where you consider two atom unit cell and half of the atoms, one sublattice moves against the other sublattice. It's called off-centering of the two sublattices, and that opens up a gap. You will see electronic band gap opens up as soon as you displace these atoms, and once you relax the structure to stable form, the phonons are all stable. Yeah? So this confirms that the antimony in cubic structure is unstable, but it can stabilize if you break its translational symmetry. Similarly, you can also use chemical field to break symmetry, and that's where we get connected to the chemical bonding. The chemical field is basically anti-SB gets replaced by Bi and Sb in a continuous manner like we show here, and there also in the electronic structure we open up a band gap. Yeah? So this convinces you now that the ground state was unstable, highly degenerate, and Peierls-like mechanism allows symmetry breaking to open up a gap and go to lower energy state. In fact, now we can look at the evolution. It's a structural evolution from covalent state to metavalent state, and look at the epsilon infinity, the dielectric constant, which I told you was very anomalous for metavalent state. Indeed, there is a discontinuous jump in it, and not only that, the slope of this is much higher than the variation in dielectric constant in the covalent case. It confirms that the transition from covalent to metavalent bonding is discontinuous. And not only that, in fact, we predict another property. The second derivative of this dielectric constant with respect to structure gives us second order Raman tensor. And what is fascinating about this bonding is now our theory allows us to predict yet another anomalous property, that nonlinear response here is stronger than the linear response. In this case, second order Raman is going to be more intense than the first order Raman in these compounds. Yeah, so and that's something we will wait now for experimentalists to verify. I think I'm running, I have 5 more minutes or, yeah, okay. So we also look at the evolution with chemical field, which allows us to go from metallic state to metavalent bonded state to ionic state. And in this evolution, again, you will see metallic state is basically singularity in the dielectric response, and ionic case involves a slope discontinuity in the transition in terms of dielectric behavior. Okay, so this sort of tells that ionic and covalent bonded states are qualitatively different from the metavalently bonded state. It involves discontinuous phase transitions. We look at the energetics as a function of structural evolution, and here we compare all covalent and ionic bonding materials as well. And the key feature you will see is the cusp is only occurring in the metavalently bonded structures, which are basically SB and late telluride. Yeah? So indeed, these materials are very unique in terms of electronic behavior, structure, properties, and also the energetics. So we then have this phase diagram, which is we have plotted, which guides now chemists and physicists to develop new materials which will exhibit this type of bonding. So just like in physics, we have Big Bang theory, and then spontaneous symmetry leading to formation of different particles. Here, this point is the metallic state, which is high symmetry state. It breaks symmetry along both x and y axis and transforms to metavalently bonded states. And if the symmetry is broken even further, it transforms to ionic and covalently bonded four-fold coordination structures. Indeed, the metavalent bonding comes as only in a small region. By the way, there are sort of broken axes here. Metavalent bonding is stable only in a small region which corresponds to very weakly broken symmetry of the parent metallic state. Yeah? So this is sort of the picture we developed from our analysis, and I'll now skip some of this, but only to tell you that we can also derive a very precise picture of this bonding now using the tool what is called as one-year functions. One-year functions are like molecular orbitals of extended infinite crystals, and the key feature we find is, this is the tellurium p orbital, which is bonding with sigma with the next neighbor, but then the next neighbor shell is anti-bonding. Sigma star is anti-bonding. And same with pi, you have alternating pi star type bonding, which means the bonding involves extended electronic interactions which run over at least 5 atoms in each x, y, and z directions. And that's why same electron is involved in bonding different pairs of atoms together, and as a result, with fewer number of electrons, the crystal is able to support multiple number of bonds. And now the last sort of point is, where does that very anomalous dipole moment or bond charge comes from? So here what we are showing is the one molecular orbital for undistorted structure, and on the right we displace lead atom to the right to create a positive dipole moment, and what you will see is there is a charge which transforms from the right lead atom to the left lead atom, electronic charge. See, the lead is a positive ion which is moving to the right, and small amount of electrons moves across the whole unit cell. So although the charge is small, it generates a huge dipole moment response. And same here with the pi channel. Okay, so this explains why the bond charge, the dynamical charge of these compounds is 8, not 2, and the reason is there's a long range charge transfer which generates these type of effects. So this is the sort of beautiful picture we derived, a simple picture of this bonding, particularly depicting the response of these compounds to any electric field or polar field. You apply electric field to the right, an electron, a tiny amount of electron hops from lead to tellurium and then tellurium to the next lead. So it's an opposite motion of electron, very tiny charge, but by almost 1 unit cell. 1 unit cell is like 5 angstrom. Okay? And as a result, you get very large dipole moment. In physics language, it basically means the bond matrix element between this, the transition element is large, which is not our result. This was seen in PRL 2007 earlier. Our picture explains why this matrix element is anomalously large and hence the properties. I'll summarize my talk here. First is basically the metavalent bonding comes about as a weakly broken symmetry state of a parent metallic state. Second is its multi-center bonding, which is why it explains these properties. And lastly, the long-range charge transfer is the mechanism which governs its very anomalous properties involving responses to polar fields. Yeah? And the take-home message is different chemical bonding in these systems, at least, we have shown is a consequence of broken symmetry, very similar to the high-energy physics ideas that we have. So I thank my student, Ragya, and Professor Rao. He is the one who posed this problem to us as a challenge, and it took us about 2 years to develop some understanding about it. And thank you for your attention as well.